So this is the latest testing with the AIS marine traffic data management. My strategy here was to create a series of key aggregation dimensions. So that would be the zoom or the scale, the X, Y, and Z positioning, as well as time. So if we can create a bin on each of these, we normally have for WebGIS zoom levels ranging from 0 to, well, if you went to 24, you'd be talking about a quarter-meter resolution in a low latitude. So we had a couple of challenges here. We want to have an equal area projection on our coordinates so that when we bin the data, we have relatively consistent binning dimensions. And then we're going to convert those binned data back to, well, not back to, but into pixel coordinates. So we'll want to have the addresses for any zoom level. We'll have the X, Y, and Z bin values as well as time binning. And so this is going to get kind of interesting. As you're reading the data into any given system, my strategy here would be to round the data. So I'll show you that in just a minute. But first of all, let's go ahead and walk through the overview. So I created an AIS class to test with. I'm going to use multiprocessing. So in this wrapper script, I'm basically just calling back to an AIS library that I've been developing that will go out and fetch the data, and it can bin the data as it streams. It can also aggregate on demand or programmatically, as well as process the data. So here we go. Let's give it a start. First thing we're going to do is we're going to look at the directory structures that we're going to use. If you're not careful, if you have a high resolution and a large region, it can fill up a hard drive. So make sure you have plenty of space if you're going to tweak the parameters for binning to be somewhat small. I tried this with rastering as well. It works, but it just takes several hours to render an image for a single day of AIS traffic for the entire U.S. So that's Alaska, Hawaii, Puerto Rico, and mainland. In any case, what I'm going to do here is I'm going to skip over the downloads that we already have the data. This only takes about 10 seconds anyway per day. So it's not that big a deal. I'm managing all of the CSV files from marinecadastre.gov as compressed CSV files, so they're zipped. We don't have to unpack them. I'm using Python's pandas library. It can read them direct. It can also do the same thing with the geotiffs. You want to be sure to compress everything every chance you get. Or in this case that I'm going to show you today, we're not going to be creating any geotiffs, any CSV outputs. We do have the option to create a SQLite database as an output. And what I'm doing that for is to catch the aggregated data, so the data in these bins. So moving along, I've got a multifold loop for the year, the month, and the day. If the date does not exist, like February 31st, for example, it will just skip on to the next one. It won't crash. It won't create a product. So here's the meat right here. We're going to go into our AIS class, and we're going to run multi-processed rather, one per day. So a whole day of AIS shipping traffic is what's provided from the Marine Cadastre website, and then they have daily downloads since 2018 in the same format. If you go before that, you'll be looking at a different CSV structure. So anyway, all we need to do is pass off the year, month, day, and a couple of optimized flags. Do we want to reprocess the data? We do. Do we want to save anything? We do not need to. So here we go. The rest of this is just management of the loop. Now we're going to look at our class. So we are going to be using NumPy and pandas, and we're going to be doing a little bit of image processing on the downstream. We are going to do all of our reprojection with PyProj. And as I mentioned before, we're looking at SQLite for optional database outputs. I am going to use the SciPy library for handling a sparse matrix. Basically because based on the bin sizes that we have here, we're going to determine which bin any given data point would be in. And then that's going to create a sparse matrix. If we did the full matrix, we would run out of memory at any scale because we're going to do this for the entire United States. And then on the downstream, I've noticed because we're going to be dealing with pixels in our outputs, sometimes they're just too small. So you might want to apply some smoothing to the image in 2 dimensions so that you can enrich the color a little bit. We're not going to use that in this case, but it is in there. If you are generating geotiffs, which we're not going to do in this example, that's why we have raster IO. This is the equivalent of GDAL's raster manipulation. So we are first going to set up our data so that these are the fields that are in the AIS shipping traffic data files. We want to set some error control, so we're going to set the conversion of strings to the appropriate numeric format if necessary, or string format. We're also going to set the data types if we export to an SQLite database. We'll do that here. And then we get into the meat of this. So if we needed to synchronize the data, as we saw up here, if we were going to download true or overwrite or both, that would be handled in the sync AIS. So what it does is it takes the year, month, day. If the directories do not exist for the outputs, it creates them. It reads the URL. You can, using pandas, actually read this direct. You don't have to download the file to import it into pandas. I am going to download the file because I'm trying to be respectful of the marine cadastre server and not hit it every time I want to test my script. So in any case, that will synchronize the data for you. And then here is the essential meat of what we're doing in pandas. So we're going to pass the same information, the year, month, a day. It's going to call out to that synchronization function that we just looked at. And really, the output of that are just the file paths. So even if we're not downloading anything, it will provide us with the relevant paths for the source data file, the working directory or database file that we would use, and then where we would want to archive that. That's our storage. So if we do have a file to process, because as I said before, you can create dates that are not necessarily existing, that translates to files that are not necessarily existing. So if it provides us a file and it does exist, then we're going to go ahead and work with it. If we don't have an output, we'll create it. So in any case, what we're going to do is we're going to read it in. This could be the URL or the file, as I said before. We are going to convert the coordinates to meters. So they're going to go from a geographic projection to a Lambert equal area. And what that means is that when we create bins, they will be approximately the same size bin anywhere on Earth. That's why we're not going directly to pixel coordinates, because we want the bins to be meaningful. And the data is going to populate the bins on its own. So we're not actually going to go and do any searches and lookups. As the data streams in, we're basically just going to round it to the dimensions of what I'll call a rounding cell, which is essentially a bin. So they're data driven, they're intrinsic to the data, and they're determined by the data. Also for the time management, we're going to go into epoch time. We're going to convert the timestamps into epoch time. The timestamps are in UTC, and we're going to keep the epochs in UTC. Next, we're going to move into the bounding box ID. This is what I'll unofficially call my aggregation keychain. This is where I would get the bins from the data. When we go back to here, these are the sizes of the bins, but the coordinates now will have to be determined from the data. So if I look at that function, dbox ID, let's just see what I'm doing in there. Here it is. So in the X dimension, I'm going to read the coordinates in meters. Excuse me. I'm going to take the minimum of that value scaled to the bin size. So this is how I can round to the nearest bin dimension, for example. So the bins don't necessarily have to be integers. We could round to the nearest half, quarter, etc., etc. So min and max. So this will bound our coordinate in the x dimensions. So we'll take the center of that as our output. So if we had 100 points in one bin, the center of that bin would be the new coordinate value for all of those points. We're going to do the same thing in the y direction. So the northings would be our equal area coordinates in meters. And we'll bound them now in x and y. And then we'll also do it in time, and we'll use the epoch for that. So this is going to be meters, and time is going to be seconds, as we had from our bin size. So you can play with those here, and it will rebin the data on the fly. Okay, so that's what bbox ID does. So moving back up. Next thing we'll do is, I have noticed there are some typos in some of the AIS files, so we'll fix that. That's what this is. I have also noticed there sometimes are airplanes with AIS transponders on them, and their velocity is very high, and it throws off the color scale. So we're just going to put a cap on that. So if there are aircraft in the area, their color would be the same as a fast-moving ship. And I'm being nice here. I'm giving it a nice generous value. Then we're going to order the columns to match the AIS. This is an optional step. If we are saving the data, then we'll go ahead and write that database out. This actually happens very fast. So in about 20 seconds, I can download, bin, and save 1 day of AIS shipping traffic, which is about 7 million data points, or about, let's see, a few hundred megabytes of compressed CSV. Then we're going to aggregate the data based on those bins. So now we are going to look at the aggregation function. So the aggregation function creates another pandas data frame. We can write that to a database as well. So that's included in my time. So we're going to actually get two types of databases, the raw unparsed data and or the aggregate data in two separate files. However, what are we aggregating on? We are just playing with a test here. We're going to aggregate on the bins, all three of them. So bin X, Y, and T. And if we had a Z bin, we can put that in here as well. And we're going to aggregate around the speed over ground. So we're going to set that as our key. And with speed over ground, what we're interested in are per bin, how many points were in the bin, what's the minimum speed, the maximum speed, the average speed, and the standard deviation of speed. We're not going to use all of those in our example, but they are available to us. And then we're going to reset the index on that because they will not be available as columns unless we do that. Then we're going to rewrite that whole thing out. We're going to have a new pandas data frame with bin X, bin Y, bin T, the average longitude, the average latitude, this is relative to the speed over ground, the count, min, max, mean, and standard deviation. And once we've done that, we're going to send that over to our tile script. So I have a couple of other helper functions in here we don't need to get into. If you are outputting a geotiff, that can be handled with this function here. And you just uncomment that here. And you can run both of these together, the geotiff and the tiles, or one or the other. Doesn't matter. So let's go to the self.tiles. And that's here. So first thing we're going to do is we're going to join those two pandas data frames into a new one along their common bin. So we're going to take the source data, and we're going to take the aggregated binned data. And we're going to go, and our goal here is to recover those original coordinates in latitude and longitude, and then append those to the bins. If you remember just a few moments ago, I said that we had our average positions. Those are the centers of the pixels. Now, I'm sorry, those are the centers of the tiles, but that's only going to provide 1 point per tile unless you put or yes, that would provide 1 point per bin. Sorry, not tile. And I don't want to see that. I want to see the original data at its full resolution, but I want to impose the attributes of the bins. So in this case, for speed, I want to see the average speed within 100 meters in 2 dimensions, and I want to see that over a 24-hour period in seconds. Okay. Now we're going to loop through each zoom level, creating all of the tiles at each zoom level. This is where it gets interesting. This doesn't have to be done all up front. This could be done on demand if the front end was sending the signal back saying this is my bounding box and my zoom level, then all of the tiles can be created much more efficiently. But we're going to go ahead and do the whole thing here just for proof of concept. So we first want to get those tile addresses for the positions in the joined data set. So we're going to convert these to tile coordinates. And then within each tile, because each tile is 256 pixels in both dimensions, then we're going to create the inner coordinates, which are the actual coordinates of the pixels inside of a given tile. So we're going to have a tile address and a pixel address within a tile. And then we're going to group that on the tiles. So we're not aggregating, we're just grouping here. And then we're going to process on that. So the aggregate was already performed outside of this step. So it's all available to us, but now we've just grouped it into the bins. So we're going to create normalized counts, normalized count of data points within a bin for the speed attribute, normalized average. So these are all going to go from 0 to 1, and the normalized standard deviation, just for coloring, because this is going to be our red, green, and blue channels. So we're going to go ahead and do that for every pixel in pixel coordinates within each tile. Now, if we needed to do any smoothing, as I said at the earlier part of this talk, we could. I've commented that out here. So we're going to look at it without any additional processing. It's just binning and assigning the attributes of the bins to the original locations of the data points. And the original data points are going to show up in the output, but the bins are going to change at the bin dimension intervals. So once we have created our red, green, and blue channels from our counts, mean, and standard deviation of speed, then we're going to add an alpha channel for all of the areas where there were no data points. So empty pixels will not show up black in our output. They will just not show up at all. And that output image will be saved. And each output image will be a zoom at a bin in time and in space. And it will have the appropriate coordinates. So now the part that we're interested in is how long this takes. So we can go ahead and run it. What I want to do first is I want to show how long it takes to get things rolling here. So I'm going to move over a directory to give you an idea of that. And we're going to let her rip. So we're going to process it, and what's going to happen first is it's going to go and fetch the file. This could be from the URL or from the hard drive. It will read it in, it will aggregate it, and it will save. So the first thing you're going to see pop up here is our aggregate SQLite database. This is all of the binned data. And my drive is on a network, so I am actually copying this file into memory from a networked hard drive. There we go. We've created that database. It's just dumping the journal in right now. So that's reading, binning, and writing out a file. Next, we are moving into the actual processing steps. We're going to go into the tiling phase, and you'll see that'll start creating the tiles here. So let's look in the tile directory, and we have one of those as well. And you can see we're already at zoom level 6. So at this time, let's go ahead and take a look at this data. So let's switch over to QGIS. And what I've done here is, because these are zoom tiles, I've created a XYZ layer. Just want to show you what's in there. I'm actually hosting it locally. So this is the timestamp, the epic time, the zoom level, the X bin, and the Y bin as tile coordinates. And there's no authentication or any of that here. So this is accessible as a web product immediately. And here we go. So these are the tiles at the different zoom levels. So what's going to be really interesting here is as we zoom in, you'll see that it's quite responsive. And this is where smoothing might come in handy because these are, as pixel coordinates, they are quite tiny. And the more you zoom in, the harder they become to find because they scale as well. These are spatial, but they are also pixels. So as you zoom in, they become more and more dispersed. So they appear to disappear. And there you have it. They are immediately available. Well, nearly immediately available. And so that is for the entire US. It's that fast. So there's a lot of information you can see. You can see there are ferries all up and down Long Island. You do get the colors. The red points are vessels that are stationary. You can see the colors, the attributes based on the speed statistics are showing up here as well. And you can even see all the interior, the shipping traffic along the rivers, the interior of the US, on up into the Great Lakes. So what does this give us? This gives us a impeccable fidelity. So if we zoom into the anchorages, for example, off of Galveston, Texas, we probably want to wait. Let's see what zoom level we're at so far. We're at level 12, and I think I have this going to 16. So this is where it becomes important. If my front end, in this case QGIS, we're sending its bounding box and the zoom that it's interested in, or the scale that it's interested in, I could just generate these on the fly, and it would be nearly instant. Using the same protocol, so just make this a CGI script. So I might lose these, but you see, I can see who's on anchor. So I'll get those crescent shapes. We're not ready to go beyond that zoom level, but we could zoom all the way into the individual data points, is what we're seeing. We're not bogging down our memory. This is quite performant in this case. We have everything that we're interested in, and we can apply any algorithm or any combination of attributes in the way that we're doing this. Because while we're creating the tiles, once we've aggregated data, then we could do anything we want with it. So we can put other things in these color channels, or we could take a single attribute, put that in there. What I'm probably going to do next is create yet another set of tiles, or maybe integrate in here a hillshade layer, which is a grayscale or an intensity map that I'll superimpose on top of these. And the reason I was thinking of doing that was for this. Let me bring another window in. This is an area off of Alaska, and you can see clearly the inferred fairways and anchorages by adding the grayscale intensity or the hillshade on top of the color. So here's the initial heat map. This is with just point density as counts per bin. Same bin, 100 meters, as we were just looking at. But this took several hours to generate because it is rasterized all up front into a geotiff. And then here are the attributes. So we can see that as the point count gets mapped into the red channel, it imposes a reddish tint wherever there's a lot of data. The green is the average speed, and the blue would be the standard deviation. So if there's a lot of green, that means that there's not a lot of red, or there's not a lot of data points. And if there's not a lot of blue, that means the speed is pretty constant. So green would mean there is a density of traffic. It's lower than in the shipping channels, and it maintains a solid speed. Blue or purple would mean speed is quite variable, and a deep red would mean there's a very slow or stationary position. And you can see how things start to interrelate. And then when you put the hillshade on top of that, then you start to get the inferred information as well. So shipping channels, places where people hide out and kill some time. Either they're waiting for access to a port, or they are avoiding a rough sea, or any other number of uses there. So this is why we want to map attributes into color, and we have an extra dimension here. So this example used 5 bins actually, zoom or the scale, the X, Y, and I'm sorry, I lied to you. 4 bins, zoom, scale, X, Y, and time. And we could add depth in here as well. So if we start working with 3-dimensional data sets, we'll be able to do that just as easily. So that's where we are right now. This was a proof of concept. I'll share the scripts out. And thanks for watching. And I'm looking forward to any feedback you might have on this. Thanks again.